Hello, I'm Tom Roddick from the University of Cambridge, and welcome to my talk on predicting semantic maps from images. Autonomous vehicles are reliant on detailed models of the world around them. These models capture both the static geometry of the scene, for example the road layout, as well as the positions of other dynamic agents such as cars, cyclists, and pedestrians. However, building such models from images is an extremely challenging task, which normally requires solving a wide array of subproblems. In this work, we represent the world as a semantic bird's-eye view map. Our main contribution is a simple end-to-end neural network which is able to predict a detailed map directly from a monocular image with no prior depth information. We make use of a semantic occupancy grid framework, a probabilistic representation which allows us to easily fuse predictions over multiple cameras and timesteps, and we show that our method is able to outperform existing works in the field. The first problem we have to overcome is how can we map information from a perspective image-based coordinate system to an orthographic bird's-eye view map? Our solution, the dense transformer layer, is based on the observation that each column of the image corresponds to a ray in the bird's-eye view space. The dense transformer uses a single convolution layer to encode each column of the image-based features to a single feature vector. A second convolution layer then expands this feature along the depth axis. Finally, since the expanded features are still in the perspective image space, we use the camera calibration matrix to resample it into the orthographic bird's-eye view coordinate system. The dense transformer layer forms a key component of our neural network architecture, the pyramid occupancy network. The pyramid occupancy network consists of four main components: a ResNet 50 backbone network, which extracts multiscale features in image space, a feature pyramid, which provides context to higher resolution features, a stack of dense transformer layers, where each is responsible for constructing at different parts of the bird's eye view, and a top-down network, which processes features in the bird's eye view to predict the final semantic map. The output from our system is a binary segmentation map representing a semantic occupancy grid. Occupancy grids are widely used in robotics and involve assigning each location in space a random variable, indicating whether that location is occupied or free and drivable. We extend this definition to that of a semantic occupancy grid, where each location is assigned a set of binary variables, one for each object category. Using a Bayesian filtering approach, this occupancy grid framework allows us to easily combine predictions from multiple observations. This allows us to fuse information across multiple sensors or across extended sequences in time. We evaluated our method on two real-world datasets, Argoverse and NuScenes. We compare against two simple baseline methods, as well as two existing methods from the literature. We find that across both datasets, we outperform all previous approaches by a considerable margin. We also provide qualitative comparisons between the different methods, which demonstrate that our approach is able to build a significantly more detailed representation of the scene. To assess the validity of our design decisions, we carried out an ablation study on the Argoverse dataset. As you can see, the addition of the dense transformer layer, the transformer pyramid, and the top-down network all led to substantive improvements in our performance. To summarize, we proposed a simple end-to-end method for predicting semantic maps directly from monocular images. We demonstrated how to map image-based features to the bird's eye view using our dense transformer layer. We introduced an end-to-end architecture called the pyramid occupancy network. We use a probabilistic occupancy grid framework, which allows us to easily combine maps across multiple cameras and timesteps. And we report state-of-the-art results on two real-world datasets. Thank you very much for listening. Please check out our paper and feel free to email me if you have any questions. Thank you very much.